So welcome along, ladies and gentlemen, to your weekly SETI seminar. And today our guest speaker is Paul Mahaffy from Goddard Space Flight Center. We're very fortunate to have him come along today to talk to us about a Mars mission that's leaving next year. Paul got a BS with a chemistry major from Dordt College and a PhD in physical chemistry from Iowa State University. He's now the chief of the Atmospheric Experiments Lab at Goddard Space Flight Center. He's also the theme lead for Goddard's NAI node, which is looking at the evolution of organics. Paul has made a career of looking at isotopes for planetary atmospheres and comets. He was a co-eye on the Galileo probe that entered Jupiter's atmosphere. He was also a PI on the Contour 2002 Contour mission, which was planned to make it to a comet. We're hoping that he has better luck with this instrument, which is now going to Mars, called SAM, which is going to talk to us today about. That's a sample analysis at Mars, which is going to be on Mars Science Laboratory. So if you'll join me all in welcoming Paul.
Well, thanks very much, Adrian. Appreciate the invitation to talk about Curiosity Rover and about SAM, and thanks to everybody for coming. So I'm going to talk a bit about the biggest, baddest rover to go to another place in our solar system. I should mention our solar system. Who knows, maybe in some other solar system they got Curiosity 4 and 5 versions already happening. But this certainly is an advance in resources, in mass and volume, and complexity. The gentleman I was talking to up here mentioned that the MER rovers are certainly a hard act to follow, and they certainly are. And so we're really hoping to use the resources that we have with MSL, with the 900 kilograms that we're going to land on the surface, to the benefit of the really exciting science which we're trying to do. To get at these questions of the possibility of past or present life on Mars. So in the upper left, you'll see Curiosity Rover is being assembled at the Jet Propulsion Laboratory in California. I think you see that's the 70 kilogram arm with a shoulder, elbow, and wrist kind of being extended up there. I think the technician down in the lower left of that picture looks a little nervous, hoping that the software guys behind the glass there have programmed everything right. You never know, Curiosity killed the cat, and you got to get ready to jump. And on the bottom left, you'll see an artist's conception of what's a really interesting experiment on MSL. It's been renamed by a student competition, Curiosity, so I'll switch between MSL and Curiosity, Mars Science Lab, of this ChemCam experiment, which is really a way of rapidly interrogating a rock. You basically focus in on a rock that's within 10 meters of the mast, and you fire the laser, and you look at the plasma signals that come back. You analyze that with a spectroscopy. And in fact, if you want to fire the laser more than one time, you can blast off the dust layer on top of the rock and really get at the composition. So you might imagine we're rolling along the surface of Mars, and these rocks kind of all look the same. And with ChemCam, we hit several rocks in a row. And if one of them stands out, that you get a different spectral signature, that might be the rock that we take this big arm to and interrogate next, drill into, and bring samples to what's a new capability on Mars, really detailed chemistry and mineralogy. And that's what I'm going to focus a little bit in this talk. The mineralogy experiment is called ChemMin, and its PI is Dave Blake here up at Ames, right across the road. And it does definitive mineralogy. It basically uses X-ray diffraction and X-ray fluorescence. It takes a little bit of powder, it shines an X-ray beam through it, and from the pattern you see on a CCD, you can really instantly, well, with a little bit of interpretation by experts, tell what the mineral is. Our experiment called SAM, or as our deputy PI, Ken Conrad, calls it Samantha, it's a she, but it was originally named SAM, Sample Analysis at Mars. And we're looking at volatiles. Among the volatiles we're looking for are organic compounds, which is a key next step that MER really doesn't do well at all. And we're also looking at a range of isotope measurements that I'll talk a little bit as we go along here. So here is Curiosity being tested in the clean room at JPL. That's an imaginary rock. It's rolling over, and you get an idea of the size of the wheels are about 0.5 meter high, and it's rolling along the clean room floor there. Of course, we have to traverse slopes. We're designed to traverse slopes of 25 to 30 degrees, and so there they have the rover with the arm extended up and the mast up on an imaginary slope. And this is the bottom of the rover. Actually, there are 10 investigations on Curiosity, 10 experiments that are led by different scientists, and we're the last one to get integrated. That's what that big empty hole is in the right. We took Sam across country just a few days ago on a truck in less than 45 hours, remarkably, and delivered it to JPL, and we're doing testing right now as we speak in the labs down at Jet Propulsion Laboratory. And very early in January, we'll be integrating SAM in that space that they've left for it. And all the instruments will then be assembled on the rover. This is an image of the descent stage. Those red things are covers on the rockets. It'll basically slow the descent vehicle down as it gets to the surface. Some of you may have seen the animation. There's a really interesting animation on the Jet Propulsion Laboratory MSL website of how they land this critter, how they land Curiosity. As you recall, with the MER rovers, they had these airbags deploy and a spectacular bounce, and then it bounced several times, and then the airbags got pulled in. And then the rovers took off away from the platform they were landed on, and that presents some sort of challenge. And this vehicle, in any case, is way too heavy for the airbags. It would just puncture the airbags. And so there's a sky crane idea, and that is that as these, instead of landing softly on the surface like Viking did with a platform and then driving off of the platform, you slow down just before you get to the surface, just a few meters above the surface, and then you tether down the rover. And the bottommost things are the rover wheels, which have deployed on the way down. And then once the wheels touch the ground, then the tether that you tether the rover down is cut, and the descent vehicle has lost all that mass, 900 kilograms of mass, so it goes flying away and crashes, and your rover's happily on the surface getting ready to do science. It all sounds a little gee whiz, but the engineers really think that that's really the most reliable, the most safe way to get this vehicle to the surface. So it'll be a real exciting time in the summer of 2012 when we land. We launch about a year from now. A couple days after Thanksgiving, the launch window opens up, and the landing is this sky crane approach. Just showing some of the harnesses, showing the upper stage here, and you can get an idea of the sense of the vehicle. So let me shift gears a little bit and talk about what we're trying to do at Mars with Curiosity and with the payload I'm going to talk about. The idea really, again, is tied toward, the big question: is there life in the universe? Is there life in our own backyard? On Mars, which is one of the most accessible places that we can get to. Other real interesting places, of course, are the oceans of Europa, but those are probably decades before we can actually get down into those oceans and make some measurements. And so Mars we can access, and people were really interested in this question way back in Viking days. It drove the science, and there were some pretty narrowly focused life detection experiments on Viking. And to a large extent, the conclusion was that they were negative. There are a few folks who believed that the results were ambiguous enough that they might support microbial life on Mars. But in large, the community concluded it was a negative result. And that kind of shifted the emphasis over the years after Viking a little bit more toward geological studies. And then kind of at the turn of the century, everybody started realizing, well, this life question is really fundamental. It should be driving our exploration. You know, by golly, if you're looking for life, if you're trying to do it systematically, one way to do it systematically is really to try and understand the parameters of life, the biological potential. We use this word habitability a lot. Are the elements, the chemical building blocks of life, you know, carbon, hydrogen, oxygen, phosphorus, and sulfur, and some of you may have heard about life might even use arsenic a few days ago. Are they present in sufficient abundance? Are other conditions that we know are necessary for life, like liquid water and so on, present, or were they present in the past? And so that's what drove a bit the Mars Exploration Rover, Curiosity, or Spirit and Opportunity. The big question that they were looking at was, is there chemical evidence on the surface of aqueous transformation? In other words, was water there right on the surface that you could get to with an experiment? And you know, those rovers were very successful. The answer was yes. And so we're moving past that now, trying to look at the chemistry and geology in a lot more detail, and you know, get at the life question, or get at, if life isn't jumping out at us, you know, why is that the case? So we're also kind of hand in hand on the bottom bullet here, trying to look at long-term processes that influence habitability. For example, we know that you know, there's not a lot of flowing water right now on the surface of Mars. It may be very sporadically happening, but in the past there certainly was a lot of water, and in the past, billions of years ago, it's certainly likely that the atmosphere was heavier for at least transient periods of time, maybe for very long periods of time. There were lakes and craters, there were rivers and so on. And so trying to understand these past conditions and how these conditions changed over time, that's all tied to the life question, and that's what we're trying to get at with this mission. And so with our SAM, or Samantha experiment, we're I've kind of broken down the science goals into these 5 goals. And the first 2 of those really tie to the question of organic compounds. On Earth, almost anywhere you go, you find signatures of life tied up in organic compounds. Organic compounds are also made in space. For example, there's a great influx of meteoritic material that falls to the surface of the Earth, and that looks a fair bit different than the organic compounds that life makes, that enzymes make, and so on. And so the very first question is, can we find organic compounds, probably from very old Mars, preserved in sedimentary rocks and so on? And if we do, objective number 1, then we move on to objective number 2. By looking at the structure of these compounds, by looking at the types of compounds, can we tell anything about where they came from? Did they just fall in from the sky in meteorites, or did they come from microbes, for example? And key things that we might look for are amino acids. For example, space radiation makes a whole range of amino acids. Life uses 20 or 21 amino acids, very limited range. Nucleobases, carboxylic acids that are tied up in the lipids of cells, and that type of thing. So we have some real specific experiments that will try and get at the structure of organic compounds, if we're lucky enough to find organic compounds on Mars. And then the rest of the experiments really are tied to the changes in the planet, the mineralogy, goals 3 and 4, and then the changes in the planet over time. So for example, goal 3 there, look at the chemical and isotopic state of other elements that are important for life on Earth. And I'll tell you in a minute how we do this, but we look at gases evolved from minerals. We look at CO2 evolved with heat from carbonates. We look at SO2, sulfur dioxide, evolved from sulfates. And so we can tell a fair bit in hand with the Chemin experiments of what these minerals are and how they formed and so on. And then goal 5 is really tied to these long-term changes in the atmosphere. For example, the processes that remove an atmosphere from a planet, which early on might have looked a lot more like Earth, are things like, for example, it's been theorized that when the dynamo that on Earth protects our atmosphere from the solar wind, when that froze out on Mars very early on, right now you don't see plate tectonics on Mars, you don't get things buried and heated and coming back up again like they do on Earth, which is really nice from the point of view of looking at very, very old geochemical conditions on Mars. But the other thing that happened, the not so nice thing, presumably if you're a microbe, is that the atmosphere may have gotten stripped away over time by these solar wind processes, and then of course ultraviolet radiation can reach the surface and the atmosphere becomes a much thinner, a much more hostile place for life. So the goals of SAM are to try and get at some of those questions. So the other advantage that we now have going to Mars that we never had with Viking. With Viking, some of you may recall that the lander was going to land from an orbiter. They got to Mars with Viking, and there was this big dust storm, and they had, very poor imaging resolution compared to what we have now. And so they kind of waited the dust storm out, and I think there was even the president got involved in the decision of when to land, because they were originally going to land on the 4th of July, and they couldn't land on the 4th of July. And so they landed, but it was a bit of the main driver was, can we find a place where there are not too many rocks where we can just land safely? Now we have just these wonderful spectroscopy and imaging tools from orbiters around Mars. And so we really can tell a lot about the sites we're going to land to. We can detect things that are just a little bit larger than a basketball with the highest resolution imaging. And the spectroscopy really tells us something about the processes that happen. For example, recent discoveries are these hydrated minerals of clays, phyllosilicates they're called. And so there's been a quite interesting community process where whoever's interested in telling Curiosity where to go on Mars, they all get together and argue for days on end and bring forward their favorite sites. I think a few years ago we started with somewhere between 50 and 60 sites, and through lots of discussion and lots of study and lots of looking at images like this, it's narrowed down now to 4. And so the decision will be made sometime next year between these 4. Ebers Baldy Crater is a real clear evidence. You can see in the top frame on the right-hand side evidence of a delta. It's where there clearly was flowing water there. It clearly deposited these sediments. How long the river flowed there, we don't know, but there certainly was a delta there. That's a place where on Earth microbes would just love, and also where they could get concentrated in the fines that get carried along the river. On the right-hand side, you have Gale Crater. That's just a spectacular set of layered sediments. The central cone of the crater goes up 5 kilometers. So you can imagine that over the life of Curiosity on the surface, it would be trudging up this central dome and looking at all those different layers and really unraveling different periods of history in Mars, Mars's evolution there. Holden Crater was also a former lake. You can kind of see on the bottom left there where the crater got breached by a river. And in fact, if you look at it in higher resolution, the lake bed then was breached by, cut away by this flowing river. And so there were all sorts of fluvial processes happening there. And then Marth is really probably older than any of these sites. It's from very, very early Mars. And the spectroscopy just jumps out at you at Mars. There are all these hydrated minerals, a whole variety of things that are exposed that just show great diversity. And so it'll be really a challenge to pick one of these sites. And this just shows where they are. Ebers, Baldy, and Holden are kind of southern latitude, Gale a little bit north, and Marth even farther north. Shows where Viking, where Spirit and Opportunity and Phoenix all landed. So the analytic chemistry experiments that I'm going to talk about with Mars Science Lab work hand in hand with the other 8 investigations. And I mentioned already this ChemCam, this laser instrument on the mast. It'll zap a rock. But up there on the mast as well is a very high resolution camera. And so the science team is going to spend endless hours once we're on Mars looking at the images, trying to figure out what rock to go to next, trying to understand if what we're seeing in the distance is really an outcrop or not. Once we get up closer to the site that's interesting, then we have contact instruments. Those are very similar to what's on MER, what's on Spirit and Opportunity. There's a microscopic imager, which is even better than the ones that are on Spirit and Opportunity. And there's another alpha particle X-ray spectrometer, which has a little bit better signal to noise than the one that's on MER. But if you see a rock that you like, you can put those instruments right up to the rock. You can rotate the turret around, and you can get measurements. And then again, make a better informed decision if you really want to drill into the rock. If you decide that rock is really interesting, then you get this rotary percussive drill going. You sieve the sample. You deliver the sample both to ChemIn and to SAM, which are on the interior of the rover. And then we start doing this really detailed chemical analysis. The other kind of new instruments are to characterize the environment. It'll be really cool. Marty is this descent imager that all the way down to the surface, it'll be taking images and storing them. So you can kind of imagine the cool videos that'll be coming out after all that gets sent back to Earth. There's a Spanish-provided MET station, which measures winds and temperatures on the rover. It's on the mast. There's a radiation detector. That was paid for by the part of NASA that's interested in human exploration. Way down the road, when we send humans to Mars, you have to understand what radiation environment they're in and how that would impact human exploration. And then this really interesting experiment from the Russians that is trying to sense the water directly beneath the rover by looking at neutrons. And so let me talk a little bit about SAM. We're really a suite of 3 instruments. We're a mass spectrometer. Mass spectrometer takes some gas, it ionizes it with an electron beam, it sends it through a set of radio frequency and DC fields, and then we count the ions that come out the other end. And so we call that a QMS, a quadruple mass spectrometer. If we're lucky enough to find organics, and if you get a whole mix of organics, then it's hard to use just the mass spectrometer. The mass spectrometer would kind of fragment, basically pull hydrogens off one by one. And so some of the signals could be overlapping, and a trace organic might be buried in a more abundant signal. And so what the gas chromatograph does, and these are kind of standard tools used by forensic people, the CSI or those types of people who are at crime scenes or detecting drugs or whatever. They use these tools all the time. But the gas chromatograph basically runs a little slug of the gas through a 30-meter column in this case, and out of the end of the column, the pure gases come out one by one, and then they get sent to the mass spectrometer and get ionized. And then if you have the fragmentation pattern, you pop it into a database of hundreds of thousands of compounds, and bingo, you get a hit. You understand what organic molecule it is. And then the tunable laser spectrometer ties to these measurements of isotopes that I talked about. So for example, why on earth would you want to study an isotope? An isotope is really the same chemical compound, but a heavier version of it. So for example, with carbon, you have carbon-12 and you have carbon-13. On Earth, that ratio is about 90 or so. And it turns out that all sorts of biologists, astrobiologists, and so on, use the carbon-12 to carbon-13 ratio to understand different chemical processes. For example, microbes in a permafrost that are making methane, a reasonable fraction of the methane in our atmosphere is produced by microbes. A lot of the rest of the methane is produced by cows and by rice paddies and so on. But biological processes like to process the lighter isotope faster than the heavier isotope. They just like to use an energy efficient process. And so you get what is called fractionation. You get an enrichment in one isotope compared to the other, which in the case of methanogens can be quite high. It can be up to 10%, for example. Same thing with water and with CO2. Not only life-type processes, but inorganic processes can do the same thing. For example, on Mars, the deuterium to hydrogen ratio, the heavy hydrogen to light hydrogen in water, is at least a factor of 5 enriched compared to the Earth. And how on Earth might that have happened? Well, it probably wasn't biological, but as hydrogen escapes from the atmosphere, and a lot of the water may have escaped from Mars, again, the light isotope is lighter, it goes out into space faster, and so the heavier deuterium hydrogen remains. And so what's really interesting about Curiosity is, and our SAM experiment, is we can not only look at these isotopes in the present atmosphere, but let's say we find a 3.5 billion year old rock, and some of the water or some of the CO2 when a carbonate was formed is basically preserving the conditions of the atmosphere when that rock was formed. And so by comparing the present day atmosphere with what has evolved from a very, very old rock, we'll learn something about how the planet transformed itself over time. And so the tunable laser spectrometer that Chris Webster at JPL produced is a part of SAM, and it really gets at those isotope questions. Then we have a wonderful kind of sample transport system inside of SAM, the Honeybee Robotics, a small company in New York, produced. They're the same folks actually that made the rock abrasion tool on the Spirit and Opportunity rover. They basically smoothed off the rock so you could take a microscopic image of it, and it was a really, really valuable tool. So they made this sample manipulation system, and this big blue thing on the bottom slide is a carousel that contains 2 rings of 74 cups, and so one by one we drop the sample into a cup that we're going to analyze. We move it over, we lower it down, we rotate it around, we move it up into an oven, and then we heat it up in the oven and look at the gases that come up. So our experiment, SAM, looks at gases. Everything we do is measuring gases, but then of course we turn little bits of powdered rock, if we're looking at rocks, and turn them into gases, either by heating or by some chemistry that I'll talk about in a second. But by heating, take a look on the right-hand slide, that's our SAM oven, and it's very carefully designed with the heaters and the radiation shields all in their own little vacuum system, so we can get up to 1,000 degrees with 40 watts is really a trick. And this just shows a little bit better the sample manipulation system. Our little micro valves, 18-gram valves, we have 52 of those on SAM, and they were really challenged to build. We built those all at Goddard. And so it's a complex beast. We spent, once we had all the parts, we spent 1 year just putting it together in the lab. But the 3 instruments, I should say the gas chromatogram was provided by our French colleagues from the University of Paris. So this really is an international mission, an international collaboration even on this experiment. We have, for redundancy, 2 pyrolysis cells, a couple of high conductance valves, these micro valves I talked about. And then lots of heaters, because if we're looking at organics, heavy organics, we want to bring those from the rock over to our instrument, and so we want to keep all the lines hot. And we want to do this in an energy efficient way, so fighting this balance of what we can do for the energy available is one of the real challenges of this mission. So these are our experiments. We operate both on solids and on atmospheric samples. The first experiment is this pyrolysis, where we just take a powder, we heat it up, we look at the gases that come off. We analyze them both for organics with the mass spectrometer and with gas chromatograph mass spectrometer. We analyze them for isotopes, some with the mass spectrometer and some with the tunable laser spectrometer. This second one, derivatization, is really a way of getting at some of these more interesting compounds like amino acids or carboxylic acid, these things that tie more directly to the life question. And it turns out that they're polar compounds, they don't go through the gas chromatograph columns that nicely, and they don't necessarily come out of a rock without being chemically transformed. And so what we do is we have 9 of our cups, our little wet chemistry labs, where we have sealed both a solvent to extract these organics and a chemical derivatization agent to transform the polar molecules into compounds that will make it through the gas chromatograph column. Won't talk too much about the rest. The combustion experiment is really to turn refractory carbon into CO2, and then we'll send that to the TLS, and we'll get an idea of the carbon isotope ratio in the carbon. So this is just some data that we took in the lab some weeks ago from our environmental tests, and on the chart in the middle there, over about a 5 to 6 hour experiment is kind of one of this core pyrolysis experiment, which will run at night. Basically, MSL will be happily tromping over the surface during the daytime, and at night we like to operate when we're not moving. Our pumps are spinning and everything. We don't want the rover disrupting our experiment. And so we have this 5 hour experiment where we take the sample, we heat it up, and we're just following a couple of the masses. In this case, we scanned from 2 to 535 mass units. In this case, I'm just showing 3 of them. What I'm showing in the black is mass 66, which is coming from sulfur dioxide. And so there was a sulfate in the calibration sample that we put in. And so it gives off its SO2 as we heat it up. The top curve there is mass 45 from carbon dioxide. And that little purple peak is water. And kind of the full spectra at one of those spots is shown on the bottom. And so this is a type of data that we'll be getting coming off of Mars rocks. So in order to make sure that the instrument will work on Mars, we test it out in what we hope is exactly the same environment it'll see in Mars in the rover. So we built this specialty chamber where the top thermal interface is basically the thermal interface that we have on Curiosity, which is this cooling system that comes from the power system, from the RTG. It's a fluid cooling system. And then we connect up to that cooling system internally with a set of reflux heat pipes. And then we put side panels in our calibration chamber, which can reach the outside temperature of Mars, could get down to -80, -100 degrees centigrade. And we make sure that the instrument works fine in that environment. We run it in a Mars environment. We run it in about 10 millibar of carbon dioxide. We even put the minor gases in that we know are there, argon, nitrogen, and oxygen in the right proportions. And just more of the data that comes off of the instrument in the lab, and we have lots of tools that our software team has developed to look at the data, showing a mass spectra in the top middle. Before we turn on the mass spectrometer every time, if the pressure was too high, for example, if the pump wasn't spinning right or something, we wouldn't want to turn on the mass spectrometer and some detectors, it would blow it. So we turn on a little pressure gauge first, the Bayard-Alpert gauge it's called, to make sure that the pressure is safe. And so that data's on the upper right. There are separate detectors on the gas chromatograph column. That data is on the bottom left. And some of the data from the tunable laser spectrometer is shown in the bottom middle. So essentially any of the dozens of temperature sensors or power from heaters or anything, we can very, very rapidly look at the data with this system. And this is exactly the same type of data we'll be getting back from space. So images are great. We'll be getting lots of nice pictures from Mars, but what really excites us are these little squiggly lines. These red and blue lines in this case are gases, in this case carbon dioxide, coming off of what was 2 milligrams of calcite, a carbonate. And if we were to find this on Mars, Phoenix made a tentative detection of it, and there's been just a few detections from orbit, but it's something that people have been looking for a long time. And CO2, of course, in carbonate is very interesting because on the Earth, this stuff precipitated out of the oceans, and you have the cliffs of Dover and all sorts of places where CO2 was formed with liquid water. And so part of getting at the history of Mars is understanding the minerals and how much of this mineral is really on Mars. Similar compound, we put in this hydrated sulfate, and you can see the sulfur dioxide peaks coming off. Very sensitive instrument with the mass spectrometer. With the Sulfates, we can basically detect hundreds of nanograms, 10 to the minus 9 grams of this inorganic compound, which is way below the sensitivity limit of any of the other experiments on Mars Science Lab. And this is really the experiment that does the organics. And so again, we're just following one mass to charge ratio over time. And the black curve, I think it is labeled 78. 78 is benzene. We put just a few nanomoles, again, 10 to the minus 9 moles of benzene in our calibration system. And on the bottom, you can see that biggest peak there in black is benzene coming off the gas chromatograph column in a nice, quick little spike. And so you can distinguish it from the compounds that are next to it, the hexane and the pentane. What I show on the top is a bunch of other compounds coming off. And this was just a test, really, to understand our cleaning protocols. We want that quartz cup, which we can heat up to 1,000 degrees, to be just absolutely pristine clean. And so what we do on Mars is we clean it the day before. We're going to do an experiment. On Mars, you don't call it the day before, you call it the sol before. So on sol 0, we call it. We clean the cup, we put it in the oven. With little puffs of helium, we basically make sure that any gases absorbed on it come off. And then we leave it in the oven until we're ready to accept sample. We move it over, sample comes down from the arm into the cup. We move it back into our oven and do the experiment. And so you can see on the top view graph, if we just leave the cup in the oven for weeks or months, I think it was in this case, you get just a little bit of terrestrial contamination in the cup. We don't want that, and so this is really proving out that the cleaning methods are doing what we want to do. We really don't want to go to Mars and detect stuff that we brought to Mars from Earth. And so a really good job, for example, was done in this theoretical calculation, a model on the right by a fellow at Jet Propulsion Laboratory, Ira Katz. And so he's trying to predict with the gases that are coming off of the electronics and coming out of the vent in the back of the rover on a moderately windy day on Mars, how would the contaminants get distributed. And so you can see that even with a fairly small wind, if you park so that you're looking at a rock and you're downstream from the wind, the contaminants are going to blow away. And so we'll be using that to our advantage on Mars. We're looking for methane in the atmosphere, for example, which is a sub-parts per billion volume mixing ratio, very low methane. Methane is really interesting. It could come from microbes. It could come from inorganic processes. We want to validate if the experiments from Earth have really measured methane or not. But we don't want any methane that's outgassing from the rover to get into our instrument. And so what we'll do when we make methane measurements is we'll park with the nozzle pointing into the wind, with our inlet pointing into the wind, and that'll help just get pure atmosphere into our instrument. Isotopes. So the tunable laser spectrometer is what's called a Harriet cell. It's basically two mirrors. You shoot light in one end with a tunable laser, and it bounces around 51 times, and it comes out and gets detected. So in a very short cell, there's a very long path length, and that gives it its sensitivity. And in order to eliminate interferences, a very narrow wavelength is scanned where you get two isotopes of the same compound. And so you can see on the right the isotopes that we're getting in methane. We get both carbon-13, and if there's enough methane, we might even get the deuterium isotope. In the middle panel there, we get the carbon-12 and the carbon-13 in different lines. And we also get the oxygen isotopes. Oxygen has 3 isotopes, 16, 17, and 18. And so we get all of those both in carbon dioxide and water. And this is what a spectra from the TLS looks like. We bring along our calibration cells to basically make sure that the instrument's working. For example, in our calibration cell, we have a mixture of inorganic gases that we're looking for. We take xenon along, but since xenon is a real key measurement that we're trying to make in the Mars atmosphere, xenon is really interesting because it has 9 isotopes, and there are processes that may have happened early in the history of planetary formation. Hydrodynamic escape, which is basically things got so hot with a big impactor that hit the Earth or that hit Venus that the atmosphere was escaping and pulling some of this heavy stuff out of the atmosphere. And it turns out that that process would fractionate Again, it would make the lighter isotopes leave faster than the heavier isotopes. And so measuring the isotopic composition of xenon is one important measurement we want to make at Mars. And but again, if we had a little tiny leak from our calibration cell, we don't want to measure the terrestrial xenon that we brought along. So we put a big spike of one of the isotopes of xenon in the cell, so it has a real distinctive signature. So if we see something that looks like that, we say, we better just empty this cell and do the experiment again. We bring along fluorocarbons. These are things that chemical companies make. And they look like this. And we have no expectation that Mars would make those. So we bring those along just to make sure that the chromatography is working. We can put those in our gas chromatograph system and make sure that we have the sensitivity that we had when we launched the sucker. This is just showing how we tune up the mass spectrometer with another one of these fluorinated compounds. And this is just a top view of the 74 cups. 6 of them are calibration cups. 59 are these quart cups. And then in 9 of them we have these chemicals. And if you're really into the chemistry, you can read the chemical names. We use the acronyms MTBS-TFA, but if you're really interested, it's N-butyl dimethylsilyl N-methyl trifluoroacetamide, and so on. But the idea really is just to take something that'll turn these polar compounds into things that we can detect. And that particular derivatization compound is, and in fact the other one, are both geared toward amino acids. If we were very lucky and there were nucleobases or something, we'd find them. But we certainly expect there might be carboxylic acids on Mars, and we can detect those with these chemistries. And so what we do is we take a sealed cup, we break a foil, and we dump some sample in, we let the chemistry happen, and then we analyze the gases that come off after we heat it. We're bringing along also, just to make sure that there's no terrestrial contamination in the sample processing system, we're bringing along 5 containers that have some of these fluorinated compounds that the drill will actually drill into on Mars. We call these our OCM, our organic check material. And so if that, let's say we were to find a really, really interesting organic, then, that, for example, showed some structure that somebody might claim was coming from life, then we'd immediately run this experiment, this blank kind of through the system, and make sure that the same thing wasn't showing up and that we weren't fooling ourselves by contamination we brought from Earth. And so what we're trying to do, and I'll just wrap this up, talk a little bit about what we're doing with analog studies. We're running a whole slew of samples, minerals, and terrestrial analogs of Mars samples through our instrument or through breadboards of our instrument. This is a list of things we're looking at. We send people up. I've gone a couple times to Svalbard, which is north of Norway, a real interesting place where we test out some of these techniques and measurement protocols. This is an example of an evolved gas spectra showing a carbonate with some trace organics from a volcano which erupted under a glacier in Svalbard about 1 million years ago. That's a process that very likely, almost certainly happened on Mars. There's lots of ice around. It turns out the obliquity of Mars changes 100 million years or so. And so the ices that are at the pole move around, and there's certainly evidence that some of this volcanic activity that happened underneath the glaciers. And so this is an analog of a little hot spring that developed after the volcano erupted. And this again shows our surrogate for the tunable laser spectrometer is a cavity ring down instrument that we measure the carbon isotopes. This is one of these phyllosilicates, these clays, and they're just full of organics. They're very good traps for organics. And so these are targets that we'll be going for on Mars. And kind of wrap it up here with the type of organic detection that we would find really, really, really interesting. And that is if you go to one of these Troll Springs is up in Svalbard. It's the world's northernmost hot spring that people have found so far. And there's very abundant life. You can kind of see the tinges of green and so on there. And so the hot spring comes out, and there are different forms of life as they go away from the hottest part of the spring. But if you look at some of these molecules, that you extract with our derivatization technique, you get patterns that are very structured in the chromatography. The numbers there have to do with the number of carbons in these carboxylic acids. And so you see, well, you have C16, a little bit of C17, a lot of C18, carbanic C19, you have C20. And the reason is that enzymes, the little biological processes that made these carbon chains like to operate 2 by 2, 2 carbons by 2 carbons. And so you get these patterns. You would never make these types of molecules in the radiation chemistries that happen in space. And so this is a type of thing that if we saw would be really, really interesting. It might not be definitive evidence of life on Mars, but it would sure motivate people to get back to that spot and look in more detail.
Quick question. The spikes with the red dots over them,
So it's another class of compounds, but the point of this was that in these fatty acids, the series that we're looking at, they're only the odd or the even carbons are enhanced. It turns out there's other classes of compounds mixed in, but and Jen Eigenbrod, who made this, was making a point with those as well. But the point I wanted to make was that with these carboxylic acids, it's this, you either get an odd or some cases you get an even or an odd distribution depending on the biochemistry. So I'll end with this slide. I took a little screenshot of the live webcam from JPL last night, and I think it was about 7 o'clock, and there were still people working away. And so you can get on that site and look at the live webcam. Point out also that it's the year of the solar system, and so there's really a variety of themes that they're bringing up month by month on a pretty nice website down below that you might want to check out. So lots of ways to follow the saga of Curiosity as it gets to Mars and starts taking measurements, and we'll look forward to in a few years telling you all what we found.
Paul, if I can kick off the questions, you mentioned the nano sensitivity of the instrument, the GCMS. Can you give us an idea of how it stacks up against Viking GCMS and what Phoenix had?
Yeah. So start with Phoenix. Phoenix didn't have a gas chromatograph associated with it, and so it was much less sensitive. Viking had a very cleverly designed gas chromatograph mass spectrometer. With the technologies that were available in the mid-70s, it was a real challenge, and some of the stuff had to be developed specifically. For example, these turbomolecular pumps that we use in the laboratory on Earth, we've now developed those. We have 2 of them on Curiosity, and so you can get a pretty high gas throughput. What Viking did was they tried to diffuse their carrier gas for the chromatography out through a palladium membrane, and then they had an automatic valving system on the mass spectrometer that if the flow of gas got too high, they'd switch valves and decrease the flow of gas, which of course decreases sensitivity. But nevertheless, they were sensitive to certainly tens of parts per billion by mass under optimal conditions, and we're more sensitive by at least a factor of 10 or more. But we're doing, I would say the main difference is that we're able to move around and get to likely targets, whereas the Viking experiments weren't rovers. They just had to reach out at what was a very dry place on Mars and pick up what could have been a very organic poor soil. And what we're really going for are sedimentary deposits that were formed billions of years ago that we can quite likely identify from orbit. So our chances of finding something really interesting are greatly improved over Viking. And I think we're also a fair bit more sensitive over the range of compounds as well.
Well, it looks like they're doing it's either a mate or fit check that they're doing there.
Yeah, I think they're integrating the rover with the descent stage there. When I was there a few days ago, the rover was all standalone by itself. and now they're integrating the descent stage with it. In fact, about 10 minutes earlier than this, they had a platform out there, and somebody was laying on the platform screwing things down.
Well, my question is, how do you integrate your instrument if it's surrounded by this?
Oh, so the descent stage will come off. This is just make sure everything bolts together right. And we've actually taken a model of our instrument to JPL and mounted it in that empty space they hopefully saved for us. And it was very instructive because doing a dry run, you kind of find out things that you need to learn before you do the real integration.
And so that actual mechanical integration is going to take place when?
So it was supposed to be the middle of January, and I guess they're ahead of schedule. So now it's just after the Rose Bowl. Everybody's figuring out how they're going to get hotel rooms. So that's a good.
Would carbon stereochemistry be useful in detecting life?
Yeah, that's a great question. It absolutely would, and it's primarily useful for detecting, modern life or current life. On Earth, your bananas and your, all of life basically uses one stereochemistry. For those who don't know, the stereochemistry really is the basic orientation of the building blocks of proteins and nucleobases, which are amino acids, and they have a particular stereochemistry. You can imagine, it's like you're reflecting your left hand and your right hand. They're mirror images of each other, but they're different, and life only uses one of those types. So we have a kind of primitive chirality detection in that one of our columns can do chiral separations, but it doesn't work all that well for amino acids. It works pretty well for amines. And so if we were lucky enough to find some amines and detect them with the gas chromatograph, it could be that we could detect some chirality differences. It's not something that is really at the core of our science, but it's something that's really valuable to do sometime in the future. That's right.
To get back to sensitivity, it's actually two related questions. One is, can you put that in perspective? For example, can you detect, say, microbe levels in rock, for example, that have been taken out? And secondly, because we would probably expect microbes, even fossil microbes on Mars, to be well below the surface, how deep can you drill down before you take a sample rather than just taking surface material?
Yeah. The sensitivity for engineering purposes, we measure in parts per billion by mass, and we can get to subparts per billion by mass. Depends a little bit on the mass range that we're looking at. The background in the instrument is just very, very clean for heavy molecules above 90 or 100 Daltons, which is where a lot of the interesting
But that doesn't,
chemistry
which
is.
doesn't help me. I mean, I'm trying to
Yeah.
understand whether
So
you
for-
can detect how many microbes, say, in the CC of.
Yeah, for a very life-poor sample, for example, in Atacama Desert, which is one of the analog sites that Chris McKay here and Rafael Rivero-Gonzalez have looked at, even in the organic, very poor samples that we get, we see lots of organics with the technique. Of course, the more you have, then the more these derivatization techniques can kind of unravel the structure and the interesting patterns that you might see. And the second question?
About depth.
Oh, depth, yeah. That was really a big discussion point when the mission was being planned. And the European Space Agency has a mission called ExoMars, and they're trying to get down to 2 meters for that very reason, in the cosmic radiation that hits the surface. And Rick Elphick there is an expert. He can tell you how far it penetrates, but some fraction of a meter or meter is kind of the typical depth where all these energetic processes happen. Those processes can destroy organics. And so if you have a surface that over billions of years didn't turn over much, you could really do some damage to the organics. And so that's why the Europeans are trying to go deep. With Curiosity, we're going 5 centimeters is the deepest we can go. But that's not, all is not necessarily lost. There are lots of fresh craters around Mars that you can tell a fresh crater if it's not eroded in too much. And so climbing down a crater where that material has been exposed over the past tens of millions of years, for example, could get you down to those depths with exactly the same, ease. And so part of the landing site process is definitely going to be look for how many kind of fresh craters are there in the area that we want to explore.
Question?
This is more general about the rover itself. Once the site is picked, what's the speed and range of this rover?
Believe it or not, I was a little disappointed. It's a big monster rover. It doesn't go much farther in each sol than the MER rovers can go. And the reason is that the rover is still controlled by rover operators at JPL, very talented people who kind of take out a path that, even though we can go over big rocks, they don't want to go over big rocks. And so it's really what you can see from the mass that you pick to go that sol. And so it's kind of, on the order of 100 meters, maybe if you have a really good view, you could get a little bit further. However, the design of the rover itself is much more ambitious than MER was. They were supposed to go a few hundred meters in the last 90 days. Of course, opportunity is still going. But the idea really here was the landing ellipse now, which I showed on the images of the landing site. It was those little black circles. I should have mentioned that. But that's 20 kilometers. And so the design of the mission is to certainly be able to get out of the landing ellipse within the nominal mission, which is 1 Mars year, which is 2 Earth years. And so kind of on the order of 20, 30 kilometers is what we're guaranteed to have by design. But there's every anticipation that, if there's an extended mission and so on, we might go much, much further.
How fast can it go, Paul?
I'm not sure how many, I'm not sure the maximum speed. I just don't know.
One final question.
I'm just curious, is there a set of results from these experiments that if you got this set of results, you would say with some confidence there was or is biologic activity on Mars?
I would say that if we saw something like this, if we definitively proved to ourselves that it wasn't coming from any contamination that we brought to Mars, we would say that's really, really interesting, and it would probably spark lively debate over how definitive it was. But it's hard to imagine, to our knowledge, processes that produce patterns like this that aren't life. If we were to find an area very rich in organics, if we were to detect a set of amino acids, if the amino acids, again, weren't from people in the clean room leaving their residue on sampling systems and so on, if they're really from Mars, if there was a very limited set of amino acids, let's say it looked like terrestrial amino acids, then that would be really interesting. That would certainly, if it was definitive, it would suggest current life. The trouble with very, very ancient life is that radiation, all these processes I talked about, kind of change that over time. What would be really interesting, of course, is if there was a set of amino acids that was very distinct and not looking like the amino acids that we know come in from space, but was different than the set of amino acids that we find on Earth, then that would suggest that life might have emerged on Mars, but it used kind of different chemistries and building blocks, and it was kind of a different type of life that developed. So those are all kind of the most interesting results from the organic analysis point of view, I would say.
With that exciting prospect, Paul, we have a special memento of your talk today.
Thank you very
If
much.
you'll join me in thanking Paul for his great